Let's talk about something we all take for granted literally every single day. How do buildings actually stand up? It's such a basic question, right? But most of us never really stop to think about it.
Seriously, just for a second, look around you, wherever you are right now. What is it, what invisible magic is holding the roof up over your head? Because it might feel totally solid, but I promise you, every single structure is in the middle of a constant, invisible battle.
You see, every building is designed to fight against forces that we call loads. There are three main kinds. First, you've got dead loads. That's easy. It's just the weight of the building itself. All the steel, the concrete, the glass, you name it. Then there are live loads. That's all the stuff that moves around. You, me, furniture, even a huge pile of snow on the roof. And finally, you get the really dramatic ones, dynamic loads. These are the sudden, powerful forces. Think of a huge gust of wind or the violent shaking of an earthquake.
Now, to fight off all those different loads, engineers have to master two, and only two, fundamental forces: compression and tension. Compression is a squeezing force, right? Think about stacking a pile of books. That's compression. Tension is the total opposite. It's a stretching or pulling force, just like a rope in a game of tug-of-war. And believe it or not, almost every piece of the building you're in is dealing with one or even both of these forces at this very moment.
And this is where it gets really, really cool. These two forces can be at war in the same object at the exact same time. So take a look at this simple beam. When you put a weight on top, it starts to bend, right? Well, that bending action is squeezing the top part of the beam together. That's compression. But at the same time, the bottom part of the beam is being stretched apart, and that's tension. So this one little beam is fighting a battle on two fronts at once.
Okay, so we get the forces, but how do we actually build something to handle them? Well, it doesn't matter if it's a tiny house or a massive skyscraper, every single building starts in the exact same place, from the ground up, with its anchor, the foundation.
And as this diagram shows, every building is kind of like two buildings in one. You've got the superstructure. That's the part we see, the part we live and work in. But then there's the foundation, the hidden hero below ground that does all the heavy lifting. It has one absolutely critical job: take all the weight from above and safely transfer it into the solid earth.
And this photo shows you what that looks like in the real world. This is what's called formwork. Basically, workers build a wooden mold, and then they pour liquid concrete into it. That concrete hardens and creates this incredibly solid base that the entire building is going to sit on for, hopefully, a very long time.
All right, our foundation is set. It's solid. Now it's time to go up and build the skeleton of our structure, the columns and the beams.
And the mission for this entire skeleton, its one and only purpose, is incredibly simple. You just have to get all of the loads from the very top of the building safely down to the ground. That's it. That is the whole game.
The superstars of this system are the columns. These are our vertical heroes. Their job is to take all that weight from the floors and the roof and give it a direct path to travel straight down to the foundation, mostly through the force of compression. It doesn't matter if they're gorgeous ancient columns or just simple modern ones. The job is exactly the same.
But columns can't do it all on their own. They need a partner: beams. These are the horizontal pieces that do the crucial job of spanning across openings. Beams are the reason we have open rooms, hallways, windows, and doors. They carry the weight over those empty spaces and deliver it to the columns.
And this slide is a fantastic example of how there's more than one way to solve a problem. On the left, you've got these beautiful classic masonry arches. They're an absolutely genius design that pushes the load out and down, keeping the entire arch in compression. But on the right, you have a modern steel I-beam. It tackles the problem in a totally different way, using its own incredible strength to resist both compression on top and tension on the bottom. And that's what lets us build those huge, wide-open spaces we love. So our skeleton is great at handling gravity pushing down, but buildings don't just get pushed on from above, do they? What happens when a force pushes from the side?
This is the million-dollar question for any tall building. I mean, think about it. A skyscraper is basically a giant sail sitting in the sky, just waiting to catch the wind. An earthquake shakes the very ground it's attached to. So what on earth keeps these things from just falling over?
This diagram shows the problem perfectly. A simple frame made of columns and beams is just a bunch of rectangles stacked on top of each other. And if you push a rectangle from the side, well, it just wants to fold over into a parallelogram. It's wobbly, it's unstable. So how do you fix it? You have to add stiffness. And one of the simplest and strongest ways to do that is with something called a shear wall. It's just a solid, super rigid wall that refuses to get pushed sideways. The analogy here is perfect. Think about a cheap picture frame. It's flimsy, right? But as soon as you put that stiff piece of cardboard on the back, it becomes totally rigid.
That cardboard is acting as a shear wall.
All right, we've covered the forces, we've covered the basic parts of the skeleton. For our last section, let's do a quick tour of the actual building blocks, the materials we use to make all this happen. For a lot of us, this is probably the most familiar kind of construction. It's light wood framing. This is how most houses are built in North America. You're basically creating a whole skeleton out of small, repeating pieces of wood. The vertical pieces are called studs, and the horizontal ones for the floors are called joists.
Now, a more modern take on that is light-gauge steel framing. It works on the exact same idea, a skeleton of small repeating parts. But instead of wood, it's made from thin sheets of steel. And the big advantages here are that steel doesn't burn and it doesn't swell or warp when it gets wet.
And then, of course, you have one of the oldest building methods in the world, masonry. This is just stacking things up, whether it's stone or brick or concrete blocks. And these materials are the undisputed champions of compression. They can handle an unbelievable amount of squeezing force, which is why they're perfect for building massive walls and those beautiful arches.
But when you get to the really big stuff, the modern giants, it all comes down to two materials, concrete and steel. And they are the perfect team. See, concrete is amazing in compression, but it's terrible in tension. It snaps if you try to stretch it. Steel, on the other hand, is great at both. So what do? We put steel bars, we call it rebar, inside the concrete. The concrete handles the squeezing, the steel handles the stretching, and together, they're unstoppable. And this quote, wow, it just perfectly sums up the massive responsibility that architects and engineers have. It's not about making a building that stands up on a nice, quiet day. It's about planning for the absolute worst combined total of everything that nature and people could possibly throw at it. So now you know the secrets. The next time you walk into any building, I want you to look for the clues. Try to spot the columns, see if you can figure out where the beams are, guess where those hidden shear walls might be. Because now, you're not just seeing a room anymore. You're seeing the elegant solution to an invisible, non-stop battle against the forces of physics. So what hidden structures will you see today?